his hard work is very much behind this particular faculty development program, and we are thankful for you, sir. To you, sir, for this you know the guidance that you have provided us throughout this particular FTP and during the initiation of this particular FTP program. So thank you, sir, and we welcome you to the session. Over to Dr. Venkatesan.
Oh, sorry. Actually, my mic was closed.
Yes, sir. Now it is. Now we can hear you, sir. Please proceed.
Oh, I have not done anything. Just a phone call. Just I made it. That's it. Okay.
No, sir.
Every effort is okay. Yeah. Good morning to all the participants and the delegates. Just before starting the class, or like I can call it a series, lecture series. I think the most of them are faculties and are senior PhD students. How many taught vibration course as part of their curriculum? Just you can raise your hand by pressing the hand button. I will try to see. How many people taught vibrations course as part of your teaching? Just you press the hand. Okay, good. Because based on that one, I will try to. Good, Professor Srinivas. Thank you very much. Then, okay, and Guru Brahma. Okay. I think Professor Anjanil Garu, you are also teaching, right?
Yes, sir. Yes, sir. We taught already. Fine.
Yeah, 3. And Professor Dr. Rajendra Prasad also is teaching, like so 3, 4. Okay, good number of people are like around 4 people are teaching, but good number of people are not taught this course. So yeah, thanks for responding to my query. Okay. So are you able to hear me? I think I'm seeing that.
Yes, sir. Yes, sir. Yes, sir. We can hear you.
Okay, good. So I think some echo is coming.
Okay, sir. We will.
Okay, sir. We stop here. Please.
Right. So
now is it okay, sir? Now please.
So please check, sir.
Yeah. Yeah. Are you able to hear me?
Yeah. Yes, sir. Yes, sir.
Okay, fine, good. So now, just I want to give quick word. The people who taught them vibrations course, they know how to write the equation of motion and solving a couple of example problems. That's clear. So, but many times we used to ask, is it really worth? Is really worth to teach vibrations a single degree freedom system and as well as the multi-degree freedom systems? Is really worth to understand the practical problems? Okay, that is a question we used to ask ourselves. Okay, yes, from exams point of view, it's clear you need to write even GATE also there is a syllabus is there on vibrations, and scoring is very easy in the subject. Okay, so there is other brownie points, but from a practical aspects point of view, vibration has any like whatever we taught at a UG level or PG level is really worth to make some decision about the designs. Okay, that is a question we need to ask ourselves. So to answer that, what I will do is I will try to cover the subject, not that deriving the equations or something, just I will try to interpret the results. Whatever you are trying to derive the equations, from there you will get the graphs. How to interpret the graphs from a practical point of view, I will try to look at it. Okay, so before that, are you able to see a paper in front of me? Right? So,
no,
yes.
Okay, for example, I will try to take some volunteer. Anybody can become a volunteer. Okay, so look at it, this paper. So from a mathematically, I can try to represent it as a plate, a 2-dimensional plate, because the third dimension is not significant with respect to the length and width. So obviously we can assume this problem as a two-dimensional problem, right? You can assume it as a two-dimensional problem, right? So I'm holding at this end. So I can approximate it as in engineering, nothing but an approximation. So we can approximate it this as a clamped boundary condition. So in a simple terms, a rectangular plate, okay, and two edges are clamped and two edges, top and bottom edges, are free. Am I right? It's a mathematically I can write it this problem. Right. So now I'm doing a couple of motions, then try to see these observations and maybe share your observations. Yeah, so somebody can put your observations. Okay, so simply what I am doing is I made it a rectangular plate, two edges are clamped, top and bottom edges free. So I created different motions. So what is your observations on this?
The paper is moving along x direction, x-axis, and even on the y-axis, and even it is fluctuating both the x and y, by frequency, like wavy motion is also there within the body, sir.
So what? Yeah, thank you very much, madam. What I'm saying is, for example, this.
Sir, good morning, sir.
Hello.
Sir, the first case, this is Guru Brahma from CBIT, sir.
Yes, sir. Please tell me.
The first motion is a rigid body mode shape.
Maybe, may not be. Okay, fine. Yeah, combination is there. Okay, fine.
There is no. Yes, sir. The second one is there is a mode shape is existing because x and y axis. That is a rigid body, and the second type you have taken.
Even may not be rigid body also, right?
Yes, sir.
May not be rigid body because this is has some elasticities involved.
Okay, sir.
Rigid body, even that motion also doesn't have any flexibility.
Okay, sir.
But anyway, yeah, please go ahead. I can
That's it.
as an in-plane motion. I agree that this is the one.
Yes, sir.
Is
Exactly.
in-plane, right? This is in-plane.
Yes, sir.
This
There is an in-plane.
Okay, in-plane motions.
Yes,
and
sir.
this
Out of plane.
Good. So now we are talking about in-plane motions. Means the plane, which is the paper, is there, and the motion is involved in x direction and y direction, and one is out of plane. Yeah. What other observation?
What other observations?
Related to our title.
Sir, related to?
Our title. Again, I'm repeating.
Okay, sir.
Okay. So yeah, it's not wise to guess from our side, but what it is happening is, you see the motion which is in plane, the sound was not there. When I made it out of plane, you are able to hear the sound.
Yes, sir. Yes, sir. Exactly, sir. Yes, sir.
So now what happened? These three in-plane vibrations and out-of-plane vibrations are there. Okay, what are the vibrations we have not discussed, but at least we are telling there is a vibrations are there. It's in layman terms. There is a vibration is there, and in-plane vibrations is not generating sound, but out-of-plane is generating the sound. So the first observation we can say that all vibrations may not lead to noise. Okay. The second observation is vibrations creates the noise. Okay, or vice versa. Vibration creates the noise. All vibrations may not create the noise. Right? So this type of sound we call as structure-borne sound. This sound we call it as structure-borne noise. Okay, the structure is radiating the noise is the one. So one example is, for example, your bike speakers, like a horn is there, right? That is one of the example of structure-borne noise, right? So even the speaker diaphragm, that is also because of the diaphragm is vibrating and sound is generated. Okay, so most of the engineering problems they consider vibrations as the cause for the noise. Okay, vibrations cause the noise. Okay, now next one, only noise is coming because of what is the noise? Noise is nothing but unwanted sound. Noise is nothing but an unwanted sound. Okay, the sound is radiated because of the vibrations. Is the only vibrations are reason or something else? Something else is there, that we call as aerodynamic forces. So for quick understanding, you observe your ceiling fan rotations, right? When your ceiling fan is rotating, a new brand new bearings, nothing is making noise. Only the noise dominated because of the your fan blades. When you're rotating, what will happen? Your fan blades disturbs the surrounding air. Okay, that is aerodynamic forces creates the noise. Okay, that we called as airborne noise. Okay, that we called as a airborne noise. So then what will happen? Noise is coming out, but that is because of the two reasons. One is because of the structural vibrations. The second one is because of the aerodynamic forces. How to estimate aerodynamic forces? There our fluid mechanics team will help us. That is CFD they will do, or like a simple calculation they will try to come up, and they will do the aerodynamic forces. And the aerodynamic forces creates a noise that we call as a aeroacoustics. Similarly, the dynamic forces leads to the vibrations, and these vibrations leads to the noise that we call as a structure-bound noise. So now if somebody is asking me to understand the science of study of sound, the science of sound is called as acoustics. So if I want to understand the sound, I need to know what is the root cause of the sound. That may be the structure borne or airborne, and that airborne has aerodynamic forces and structure borne has the dynamic forces, and that leads to vibration. I need to understand these root causes. Then only I can answer the noise. Okay, fine. Next, okay, for this course, I will not talk about aerodynamic force estimations, those things, because that is not our scope. At this moment, our scope is vibrations. Yes, the vibrations leads to noise. And vibrations, as I said clearly, all vibrations may not lead to the noise. All vibrations may not lead to the noise. Now, how to control the vibrations? If I understand how to control the vibrations, automatically I can control the noise, especially for structure bound noise. So now the same example I'll continue. This is a plate, right? A and B. This is A4 sheet and made it off. Okay, this is a A4 width and off of this. So now just you observe carefully what I am doing. Okay. Are you able to see me now? Yes or no?
Yes, sir.
So now we observe the same exercise I am repeating now. Yeah. So now tell me, what is your observation here? What is your observation here?
Due to increased stiffness, the sound has decreased.
Very good. So what has happened? Now I change the stiffness. I change the stiffness. I change the stiffness by playing with the geometry. Agreed or not? I played with a geometry, right? So now our job is, yes, whatever the vibrations is a function of, vibrations is function of some parameters. That vibrations, okay, I will try to share my screen now. Yeah. Are you able to see my screen now? Yes or no?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Vibrations is function of stiffness, right? Right. Then next one is, okay, that is nothing but mass. The inertia will try to come into picture. That's it. Only two parameters. Okay. So now our job is how to play with this K and M. Okay. Now just a minute. I will try to see my PPT is open or not. I will try to cover it on a pen and paper, and then I will try to come back to the slides. Okay. Now, yes, we want to get the vibrations. We say that vibrations, what is the definition of vibration? Oscillatory motion of a dynamical system from its equilibrium position. There is a definition, we'll try to give it. Okay, from its equilibrium position. So now what is the oscillator? To and fro motion is happened with respect to the mean. Okay, with respect to the mean, we are doing the to and fro motion. Now, oscillator is important. Second one is dynamic is important. So what is the dynamic system? We don't know. We'll try to understand. So any dynamic system, generally we say that, okay, dynamic system has mass, nothing but inertia. A dynamic system has the inertia and the elasticity. Okay, has a elasticity. Nothing but inertia is nothing but mass, elasticity nothing but stiffness. Right? If a system which has the inertia and elasticity, and we call it that as a dynamic system, and it has an oscillatory motion from its with respect to its equilibrium position, then we call as a vibrations. Right. Now, with this a simple definition, then immediately we have a things. Assume somebody, a human being itself is like as a dynamic system. That is the reason we have our own natural frequencies, right? So, but this dynamic system, try to measure. Okay, now I will try to write it in a simple way. Okay, I have a cantilever beam, for example, assume it. Okay, I have a cantilever beam. So this as a inertia and elasticity, I will try to represent it as a lumped parameters. What are the lumped parameters? They are very mathematically, it is existing. In reality, it's not existing, right? But what it means, whatever the inertia is there, the total inertia I will represent it as a mass m, but don't have any elasticity. So I'm segregating them. I'm trying to say that, okay, whatever inertia is there in this cantilever beam, okay, write it as a mass. Don't have any elasticity behavior. Then similarly, whatever the elasticity is there, the deflection characteristics are there, elasticity is there, I represent it as a spring, and assuming that spring doesn't have any mass, only elasticity is there, right? And this is my equilibrium position. Okay, this is my equilibrium position. Okay, this is my equilibrium position. And now what I'm doing, what is the vibrations means? A dynamic system that has elasticity and inertia, and it is equilibrium with this in vertical direction. Okay, and assuming only single degree freedom. What is the mean of single degree freedom? I will try to tell that. Okay, the mathematical, the textbook definition is the number of independent coordinates required to define its position. We call that the single degree of freedom. So single degree freedom is only 1 degree is sufficient to define its position at any point. So that I am writing as a displacement x. Displacement x. Is it clear? Right. If I try to call it as a displacement x. Now this is to and fro motion is happened. Then we call it as this system called spring is there, mass is there. How many degrees of freedom there? 1 degree of freedom there. So we call it a single degree of freedom, spring, mass, vibration. Is it clear? This is the one we'll try to teach as part of our classes, right? Then still the assumption is now I try to disturb from its equilibrium position, it's keep on oscillating. But in reality, because of the you take a spring and attach a mass and try to pull and leave it, it keep on oscillating, right? But the oscillations, whatever you try to see, this is the idealistic world, but in reality will be like this. Means it will try to come back to equilibrium over some time. This is like is the amplitude of vibrations. Okay, this is the as function of time. This is the amplitude of vibration as function of time. What happened? It will try to decay. Amplitudes are decaying, right? To define these characteristics means the amplitudes are not sustained at the same level. It is try to decay it and come back to equilibrium position. So what you are doing, you are trying to dissipate that energy. To represent it, the more simple way we call it as the assumption we make it is a major assumption. The dissipation capability, we write it as a damping, and the major assumption is viscous damping. Okay, viscous damping. So what we say, the dissipated forces is a proportional to the velocity, that we write it as Fd equal to, okay, C into some constant. We are replacing the proportional, that we represented as C, that we called as a damping coefficient, that we call it as damping coefficient. C is called damping coefficient. Right? Fine. Next. So we introduced the term called lumped parameters. Then we introduced the mass, the elasticity behavior is expressed in terms of the stiffness. The dissipation capability of the system is represented in terms of the damping. Right? So this is Fd Cx dot. Now, if you see the spring force, we know that the spring force is a proportional to the displacement. So what does that mean? The spring force equal to K into X, right? That K is called as a spring constant, right? Then next, inertia force, mass into acceleration. That is nothing but mass into X double dot. Okay, so then M is mass, right? So to incorporate all these things, now rewrite the same one. There is a spring. The dissipation capability as a dash part will try to dissipate it as a stiffness, stiffness spring, and that dash part with a damping coefficient C and connected to the mass M. Right? And it is under influence of the external force and oscillating. The displacement we are writing as X, right? And there is an external force is acting on the system that called as a F of T, right? So now what we can call it as F of T is the external force. These are external forces. Okay, so the basic framework we try to establish for the writing equation of motion of a dynamic system, we are able to get it. So here before going further and understanding this system response under the influence of external force and no external force. So yes, if this is external force, we call it as forced vibrations. We call it as forced vibrations. If external force is 0, then it is called as free vibrations. It's called as free vibrations. One is called as a forced vibrations, other one is free vibrations. I think I mentioned in last class, but again I will repeat it. Okay, the free vibration and forced vibration, the good example is the student's behavior in a classroom. Okay, in the presence of the teacher or in the absence of the teacher. In the presence of the teacher, in the absence of the teacher. In the absence of the teacher, the student will try to respond according to his own natural frequency. Okay, some students will keep quiet and they will not disturb anybody and they keep quiet. Some students will try to talk to only with their neighbors. Somebody will try to get attention of everybody, okay, by doing halla. So then what it means? So that their own natural frequencies. But in the presence of the teacher, everybody wants to listen to the class in hypothetically, okay? In the on paper, they will try to observe the teacher. So what it means? That is under influence of the external forces, right? So then if you want to understand the natural frequencies, the natural behavior, you need to eliminate the external force. Then it will try to respond. So that is the reason whatever you try to do it as part of the free vibrations, what outcome you will get it? Natural frequency. Okay, that is the one you will try to get it. And later we will understand the mode shape, the relative displacement, that is the one, and damping. These three are the outcomes from your free vibration analysis. In the forced vibration analysis, it will try to respond to the given exponent. So then obviously it will be mostly vibration response. Okay, vibration response. So vibration response, it may be displacement, velocity, or acceleration. Okay, any doubts till now? Okay, if you don't have any doubts or questions, so then we'll continue further. Okay, fine. We are talking about the external force, but we have not made any comment about external force. So we'll try to comment it on external force. Before that, just we will see in a mechanical engineering, only the two parameters are important. Only two parameters are important. One is the force, other one is motion. Okay, only the two parameters are important in mechanical engineering. Okay, one is a force, other one is motion. Okay, one by one we'll try to talk about it. If I don't have a force, only motion is involved. Only motion is involved. Okay, there is no force, only motion involved. What type of analysis we call it as? Generally we'll do in engineering mechanics course, that we call as kinematic analysis. Yes or no? So in a kinematic analysis, what we'll do, we'll try to get a displacement, velocity and acceleration informations. Right? Mostly the motion related parameters we'll try to get it. The second one is motion is not there. Okay, but only the forces will try to do that. Okay, can you give me what is example it is? Then the third case, I have a force and motion is involved together. Okay, next one is I don't have force, I don't have motion, but still I am doing design. That is called as styling. Right? That we call as styling. Then if you have force and motion both are involved. Okay, force and motion both are involved. We call as dynamic or kinetic problems or dynamic problems. And they are varying with respect to time. So then we call as, okay, your force is there. Even motion is also involved, but force is not varying with respect to time. Then we call it as static problems. Okay, motion, because I can't say that motion is not involved, it's there, but f of t is not equal to 0, then we call it as thing. Fine. This is the one we'll try to teach as part of the strength of material course. The styling generally as a mechanical engineering point of view will not do it, but other design, the product designs, aesthetics and those things, the styling of the vehicle will come into picture. So to get an idea, I will go to my slides. Okay. Are you able to see the slide?
No, not yet, sir.
No, sir, not yet.
Okay. Now?
Yeah, yes, sir. Yes, sir.
Okay. Right. So what we are talking about styling is there is no forces, no motion. The static forces generally is the forces are there. Generally, as part of the strength of materials, we'll try to talk about the static problems. Motion, right? What we'll do here, we will try to do mostly force balancing, and forces are not involved, but only motion we are interested. This is called the kinematic studies, and both are involved. We call it the dynamic studies. So the forces are varying with respect to time. Now, yes. Then we try to talk about it. Yes, the dynamic system, which has the mass properties and as well as the relative motion is there. Means obviously it's not a rigid body, it's an elastic body. Then we'll try to do that. Okay. So for these problems, we'll try to study it. As I said, I will come back to again on the my notes. So we are considering only the dynamic forces. I hope you are able to see the nodes.
Yes, sir.
Right? Yes. Okay. Dynamic forces. Now what we are telling is the forces are varying with respect to time. Right? Then immediately question is, sir, can you tell me one example of the force where the force is not varying with respect to time, other than the gravity? Okay. We are assuming the gravity forces are not varying with respect to time. That is the one, it's fine. But other than the gravity, is there any force it's not varying with respect to time? Is there any force is not varying with respect to time? Not possible, right? Right? Not possible. So almost all forces are varying with respect to time, except the gravity, I said. Right? Then obviously the static analysis, whatever you are trying to do a strength of materials is useless. Right? But it's not true. That is a fundamental course we are trying to teach at the second year, or when you after joining engineering, that is the one we try to teach. Right? What is the why we need to do that? Why can't we start dynamic directly? The reason is engineering nothing but an assumptions. Engineering nothing but an assumptions. Okay, engineering nothing but an assumptions. So what we are doing, we are making a major assumption in this. What we are saying is, whatever the force, okay, you try to apply a force, it has some frequency omega on a system, a dynamic system. This dynamic system has a natural frequency omega n. Okay, if my applied frequency omega is, generally the rule of thumb is very small, means my system is trying to respond at a faster rate than the applied force, then we can approximate it as a static problem. Is it clear now? So my applied force omega is very, very small, means what happened, the time period is very large, means my force is varying very slowly, right? Then and with respect to the natural frequency of the system, right? Imagine another way. For example, sometimes the life, you meet somebody, he interacted with 5 minutes, okay, and somebody is there with you for long period. So the changes, okay, our best example is the corona time. You met your friend before corona, after corona you met him, right? Maybe I hope in the next month or another month, maybe we be relaxed from all these pandemic constraints, but you try to see your friend, right? Then surely you will see a changes in his anatomy. Yes or no? State of mind, I'm not talking about it, but I'm talking about anatomy. He may be put up weight, or so you are able to see the changes, right? But if you try to see him very regularly, obviously your observation period is very, very small with respect to his changes. Then you feel is more or less, it looks the same. He may not change. You can't ask your colleague, yesterday you are more weight, you are fat, today is small, or you are thin to yesterday and today you fat. Like that, we can't comment it on your day-to-day people we are interacting, right? Right? Only we are seeing that yes, the changes with respect to changes your observation period, okay, will come into picture. So relativity will be there. So obviously that relativity we will try to use it for getting the static problem versus dynamic problem. So we classify the static problems where the applied means the force frequency is very small with respect to approximately, I'm telling 1/3 of the natural frequency. We can approximate at those problems as the static problems. Right? Then we are not talking about the time into consideration. Does it make sense? That, okay, fine, sir. We are talking about a time into consideration. Yes. So I have taken a problem where the omega is a little bit like above omega n by 3. So this we call as a dynamic force, dynamic problems. So then what I applied this. So what is the response I will try to get it? I will get a displacement, velocity, and acceleration. So first derivative of the displacement gives me velocity, second derivative gives me the acceleration. But if you observe the displacement, that is varying with respect to time and with respect to space. For example, I have taken a plate, example I have given, I applied a force F sine omega t, okay, then this as a function of time it is varying, and as function of position also it's varying. Agreed or not? So obviously my displacement is a function of space and time. Okay, my displacement is function of space and time. So imagine another analogy. Okay, somebody called you and asked, where are you? Okay, where are you? What is your answer? What is your answer?
You tell the place.
Somebody called and said, where are you? What is your answer?
You tell the place, sir, place.
Huh? You will try to tell that
Place.
place. For example, something I'm at home or something like that. But there you are making an assumption. What is the assumption you are making? About the time you are making assumption, you are assuming at this moment, right?
Yes.
I'm little bit offset guy. What I will do? At what time? right? I want to irritate my friend. I said at what time, right? So then obviously what happened? He has to give the time coordinates. Okay, fine. At this moment or yesterday evening, something like that, right? Or reverse. Somebody called you. I saw you in market. And then immediately ask at what time, right? So you are either you are fixing the space or time or space, right? You don't get it the two informations at a time, right? Space is independent variable and time is independent variable. So I can't take the two at a time because handling two is not easy. Yes, we'll handle it as part of the advanced courses, but in the basic level courses, we'll not handle the two at a time. So obviously we need to make some assumption. As I said, where are you means you assumed at this moment, then you give an answer. Same way, why can't we make some assumption about either space variable or time variable, right? So the biggest assumption we can make it in all the dynamic courses, okay, either in acoustics or vibration, this is the fundamental assumption we'll make it is with respect to time, whatever variable you are trying to observe is harmonic in nature. Okay, harmonic in nature. This is one of the beautiful assumption you can make it in a vibrations course. What does that mean? The harmonic in nature means as a function of time, the behavior of that particular variable is like that. Acceleration is proportional to the displacement opposite in direction. See the beauty. See, acceleration is a proportional to the displacement opposite in direction. So what I mean, if I take it as pendulum, okay, I try to oscillate it. This pendulum has a displacement and corresponding acceleration. So if my displacement is in the direction, acceleration is in this direction. If my displacement is in this direction, my acceleration is in this direction. So this is a oscillatory motion. This oscillatory motion with respect to time, it behaves like a harmonic in nature. Okay, this is the beauty of this assumption. So what will happen if I try to replace with a constant? X dot equal to some constant, I need to write it. I am writing that as a omega n square x. Right, omega n square x. So then what will happen? I rewrite it x dot plus omega n square x equal to 0. This is the equation of motion. This is the equation of motion. Okay, this is the equation of motion for for a harmonic system. Right. Then we have already written an equation of we have already written a system, a single degree freedom system, right, with a spring mass damper. What is that system is? There is a spring, there is a dissipation capability in a damper, that is a viscous damper, and a lumped parameter inertia as a m, right? Like this we have done. Fine. So under the influence of external force. So now you try to look at it, all the forces. You write it first. We assume the by using D'Alembert's principle. D'Alembert's principle will help you to convert a dynamic problem into the quasi-static problem. At that instant, you can convert it. So you apply Newton's method, and there are other ways you can do it: Lagrangian method, energy-based methods. There is Lagrangian method for the getting the equation of motion. Right now, I'm talking about Newton's method. So what are the forces are there? Spring force, damping force, and external force, and inertia. Because of this, you want to bring back. So what will happen? There is a inertia force to try to bring back. Okay, anyway, I will write it mx double dot plus kx plus cx dot equal to f. This we call it as equation of motion of a single degree freedom system. Okay, now this is under influence of the external force. Under the influence of external force. For a natural frequency, what we need to do? Okay, then we have a conditions here one by one. F of t and damping. Okay, fine. You may get an idea, sir. Actually, we already studied about condition monitoring. We are listening about condition monitoring. Why you are going back to basics, right? So, but this will help you to relate it now. Which parameter to be controlled? Okay, I will try to come back there. So f of t is not there. If f of t is not there, then what will happen? Okay, and c of x also. These two are not there. What will happen? Your equation of motion will become mx double dot plus kx equal to 0. That is nothing but x double dot plus k by m x equal to 0. Just you compare with this equation, the previous equation. What is the omega n square? If you assume the time is harmonic in nature, so obviously omega n square equal to k by m. that is nothing but omega n equal to square root of k by m. Okay, this we call it as natural frequency of a system, and this type of problems we called undamped, there is no damping, undamped free vibration single degree freedom system problems. Clear? Okay. Then next, if I have only damping is there, force is not there, this is there, this is not there, then what will happen? We got it mx double dot plus cx dot plus kx equal to 0. Okay, and then you will get the equation that is called as you try to teach the three different things: under damped system, over damped system, and critical damped systems, right? But what is the extra thing is coming is the damping force. So now if you try to observe the vibration response, it will try to oscillate it. So by monitoring my amplitude decreasing, then I can characterize a system damping that we call it as logarithmic decrement method. Okay, that we call as logarithmic decrement. So what it means, by doing the free vibration analysis of damped systems, I'm able to calculate the damping of the system. Okay, how much dissipation capability is there, I can estimate it by using this logarithmic decrement method. What is the logarithmic decrement method? You take it at two successive amplitudes. Okay, the two successive amplitude, so that will be like a e x1 x2 e power minus sorry, if it is done, then it's a 2 pi zeta approximated. Zeta is the damping ratio that we write as C by Cc, right? Clear? So what we will try to convey here is, by doing the free vibration analysis of thing, I will try to get it two more parameter. One is a damping parameter, that is in terms of the logarithmic decrement, and damped natural frequency. We'll try to do that, right? Okay. Now this is a very important point I want to bring it to your attention. So many times what the people will do, especially the students, when they're doing the FEM analysis, they especially FEM model analysis, they will do it, and they will not apply any damping, okay, when they're doing the free vibration analysis. Why damping is not important? Many times they are not able to get it. Any questions, please? Okay, so they will not apply the damping. Why? The reason is simple. Generally, damping is most of the practical problem, 90% of the practical problems are under damped systems, and the zeta values in the order of max is like 0.1. So you substitute back here. What will happen? Omega d into omega n, okay, square root of 0.99. It's close to 1 only. So it will be like a undamped natural frequency is close to natural frequency. Okay, undamped natural frequency is same as a damped natural frequency. That is the reason when you are doing the model analysis by using any computational softwares or experimental ones, so we'll assume the undamped natural frequency is same as the damped natural frequency. The reason of this square root of 1 minus zeta square. Fine. So this is the second analysis we'll try to get it. Then we'll come back to again equation mx double dot plus cx dot plus kx equal to f of t. Now we will try to do f of t is there, but c is not there. So this we call undamped force vibration problems. Undamped force vibration problems. So this we will try to introduce magnification factors. So this will try to write it in terms of the 1 by 1 minus omega by omega n whole square. We'll write it. Okay. So what does that mean? The frequency ratio is applied force divided by the natural frequency. Applied force divided by the natural frequency. So what does that mean? Omega equal to omega n is called resonance. It's called resonance. If it's less than 1, it's less than 1. Okay, less than 1. It is like a your excitation frequency is less than the natural frequency. If it's greater than 1, right, your excitation frequency is more than the natural frequency. So this is the one we'll try to teach. The next last one, the final one, is mx double dot plus cx dot plus kx equal to f of t. We'll try to solve. Output is displacement and even applied. So this we called as frequency response functions. So we'll write it in terms of the that will 1 minus omega by omega n whole square, right, plus 2 zeta omega by omega n. I don't want to derive all these things, just I want to bring your attention what we are trying to convey here. Okay, this is the way it is. Okay, this we will try to get it. Now, this equation has a lot of practical implications. What is those? We'll try to look at it now. If you look at it here in this equation, this FRF is nothing but frequency response function. So you are monitoring as function of frequency. That is the reason it is. And one assumption we made is time is harmonic in nature. Time is harmonic in nature. So what it mean? Okay. Displacement is a proportional to the acceleration opposite in direction. Right. Okay. What is the practical implications of this assumption? I will tell you. Imagine many times if you are doing experiments, you need to choose the sensor. Okay. You need to choose the sensor to measure either the displacement, velocity or acceleration. You need to choose the sensor. For measuring the displacement, mostly we have proximity probes. Velocity, velocity sensor. Acceleration, accelerometers. Right? Now, when I'm doing vibration measurements, what sensor I need to choose? What sensor I need to choose is the question will come. Or, and this is especially in industry, the people who do the CAE analysis and experiment, most of the Indian industry, what will happen is majority of the people will do simulation here. Experiments will be done in outside India and they try to talk. When they try to talk, that guy will give me the acceleration data. That guy will give me the acceleration data. Your FEM guy will try to get a displacement data. Then they will try to say, no, I can give only displacement. That guy tell, no, only I can measure acceleration. It's like a operation success patient did, right? He measured it, he calculated, but both cannot relate. Right? In that case, this assumption will help you out. Why? If I say time is harmonic in nature, what does that mean? I can write it x equal to x naught sine omega t, means sinusoidal functions, or cos omega t, or in a complex form I can write it e power j omega t. Right? So in these three forms I can write it. So when I write it in this form, the first derivative gives me, just to observe very carefully, the first derivative I am taking this complex form because that combination of cos and sine. So I can write it j omega x naught e power j omega t. So what does that mean? X dot equal to j omega x. So what is j? Is an Euler angle. E power j theta, we will write it as cos theta plus j sin theta. Right? If theta equal to 90 pi by 2, what does that mean? Cos 90 0, sin 91 1j. Right? Are you able to see my screen? Right? Yeah. What does that mean is, if I have this is my displacement as a vector. Okay, because it's a space and as a vector I'm trying to write it, and my velocity magnitude is x into omega, but that is making 90 degrees with respect to displacement. See how beauty it is, right? So what I'll do, I will get a displacement, just you multiply it with omega, you will get a magnitude, and you multiply whatever the phase angle is there in displacement, you add a pi by 2, then you will get the velocity vector. Fine. So if I am able to get it displacement just by multiplying the j omega, I will get a velocity. Then you do again the derivative. What will happen? J omega into x dot, or nothing but minus omega square x. Okay. My displacement, if you look at it that, so what I can write it e power j pi. J pi means cos pi minus 1, j sin pi this 0, so minus 1. Okay, omega square x. So what does that mean? The amplitude of the acceleration is omega square x, right? But it's making 180 degrees. Is it clear now? Right? So this is the vector diagram. So if I know the displacement, just by multiplying with omega square, I will get the magnitude of acceleration, but under conditions of harmonic in nature. Right? And the angle it is making is 180 degrees. The phase angle is 180 degrees. Okay. Now, just use with this, I will try to revisit this equation in a more practical way with this vector notation. Okay. If I try to multiply with k, what I will get? Okay, there is a external force that is making an angle theta, that is nothing omega t. So this is a vector, and correspondingly for that, okay. So I will best is I will try to explain in my PPT. That maybe is better. Yeah, any questions? Are you feeling more mathematical in nature? Yeah, are you able to see the PPT?
Yes, sir.
PowerPoint presentation?
Yes, sir.
Yes, sir.
Yeah.
Yes, sir. Yes. Sir.
Okay, so these are textbook ones. That is the reason I'm not going in that aspect. Just I'm trying to give highlights of that. Okay. So this is the one we are trying to sort it out, right? This is the equation of motion. We were able to do that. Okay. So F sine omega t we have taken as external force and mass, and this one we'll try to match it. So we have written the equation of motion. So from the equation of motion, now you look at it this vector notation. This is the force, right? This is the force. It's making F sine omega t is a horizontal projection, and the displacement is x. Displacement into stiffness coefficient means the spring constant. You'll get a spring force, right? And velocity into velocity multiplied with the damping coefficient. What I will get it? Damping force, that is nothing but c omega x. Then mass into acceleration gives me the inertia force, right? Now you have external force. So the external force is balanced by the three different force components. One is the spring force component, other one is the damping force component, and inertia force component, right? So this is like a balanced. Now the question is, many times in industry what will happen is, this is the common practice, there is a vibration problem, a resonance is there. So in a particular model, they identified that resonance is because of the natural frequency matches with that, and they change the stiffness, they changed it. Okay, or they applied a damping and the problem got solved. When you're going for next model, either scale up or scale down, generally we have a scaled versions, right? So you go for next version, what happens? They will try to apply the same stiffness and expecting the results will come in any surprise, but in reality that may not work. Okay, may not work. Then they will run around and said, why it's not happening? We did a previously it was working, now it's not working, right? So many times we said we use one technique, it worked, but next time it may not work. Then the people will say that these acoustics and vibration people are very random people. Okay, this is the great notion the outside world has, because you provide a solution that works for that particular one. Next time you go, okay, it will not work. It's like the same as a customized designs, right? It works for that solution, but not work for other solution. That is the reason we are able to do a lot of consultancy projects. Okay, yeah. So now what will happen? It's not able to do that. Why? But if you understand this graph, you will able to justify why it is not working or what is the parameter to be controlled. You will get it. Okay, think about like this. At a very low frequencies. Now I will try to add one slide here. Just taking this into consideration. Okay, fine. Think about the three brothers, right? The brothers' names called the stiffness brother, damping brother, and inertia brother. Okay, stiffness brothers. Think the three are unmarried people. Okay, the three are unmarried people. Fine, these three are unmarried. Okay, now their family has taken a loan from external agency. That is called a F, is the external agency, right? So big brother is K. The stiffness brother is big brother. Now what will happen? Just before he got a job first. So who will pay the loans? Who will pay the loans?
Stiffness.
Now I am talking about a condition omega is less than omega n. So omega is less than 1. So obviously what happened, omega is like omega is smaller. Obviously m omega square is smaller, c omega x is smaller, but kx is independent. So obviously kx is larger. Means what I mean is my big brother is earning, right? The stiffness brother is earning. So whatever loans are there external, that will be try to compensated by the this guy, right? Okay. This means my external force is controlled by the stiffness. My external force is because the inertia and as well as damping brothers are very small and their earning capability is less. So obviously the external will be taken care by the stiffness. So whenever your excitation frequency is the less than natural frequency, so first we need to calculate what is the natural frequency. Once we know the natural frequency, what is the external load? So that frequency is smaller, then what is the parameter to be controlled? Stiffness to be controlled. Okay, what parameter to be controlled? Stiffness should be controlled. So for that reason, whatever the simple single degree freedom analysis will help you to get a fundamental natural frequency, then you can comment it, yes, my measured excitation frequency is this much and my natural frequency is this much. So it is like a more stiffness dominant region. So I have to take care of the stiffness of the structure. That's it. Okay, next. Imagine the last brother become a software engineer. Okay. His earning is more, means obviously the situation is become omega is very large with respect to omega n. Okay, very large. So obviously who's supposed to take care of the external loads? The external dues by the mass, right? But there is a situation. Is it clear now? At a very high frequencies, omega square is very high. Then obviously the inertia force is high. Then I can control it by using the inertia force, right? Imagine a situation, the earning capacity of the spring and the earning capacity of inertia are the same, means kx equal to m omega square x, right? This is we call it as omega equal to omega n, that we call resonance. What will happen? This guy is going in this way. So if you draw that graph, this is external force, the force here, right? What is happening? My stiffness force is matching with my inertia force at resonance, right? That is the reason kx equal to m square. You see here again, you look at it, omega square will become k by m. That is nothing but a natural frequency, right? In that case, what will happen? These guys will fight internal. Why I need to pay? You need to pay because whatever you are earning, I am earning, all the things. So these guys are cancelling. They are fighting each other, right? But you need to pay external loan. Who will pay there? Who will pay there? Right? This guy. That guy is called damping. Clear? So damping is a solution. Only they are internally the two brothers are fighting. At the time, this guy is a small amount is earning, but still he will try to pay external EMI for that month only. Okay, don't expect he will pay EMI for everywhere. Means at resonance condition, the family is under trouble at resonance. So at that time, you will try to take care. So that is the reason, don't misuse the damping, assuming that damping will work every frequency range. No, damping will work only at resonance. At lower frequencies, with respect to the fundamental natural frequency, will be handled by the, handled by the stiffness. Higher is done by the inertia. Is it clear now? So if you understand this graph, majority of the practical problems can be analyzed very easily and try to give a solution is a stiffness control zone or mass control zone or damping control zone. So your solutions can be provided. Fine. Next. This is the one we'll try to teach as part of this course, damping, how it damping comes and other things. Right. So this is exactly we'll try to teach in the class. Right. We'll try to decay it and other things. Next. Other problem is base excitation problems. Okay, if our base is vibrating, this is the typical problem we'll try to do for the isolated design, right? When isolated design you try to do it, so what happened, the inertia force is mx double dot, but the relative displacement of the spring is x minus y. So the spring force and corresponding damping force is there, x dot and y dot, and you try to solve and you'll get a final equation of this. So then you draw the motion, you look at it, this is the graph, you will get it. Okay, but if you observe here, are we monitoring x by y? X is the response Y is your input. So this example problem is I have a bike. Okay, I have a bike, and that when the driver is sitting, right, there is a suspension system, and the road vibrations are there. Okay, sinusoidal vibrations are there. Okay, that is the one it is. So for given y, what this guy is feeling as x, the response. So that x by y is written here. So you want to get a suspension. What do you mean? You need x by y should be smaller or larger. The amplitude should be larger or smaller to minimize the vibration transfer from the ground to the rider in your isolation systems.
Be smaller, sir.
Smaller. So if you look at it, this graph, after what frequency ratio, omega by omega n, after what frequency ratio you are able to see the reduction?
Root 2, sir. Root 2.
If it's greater than root 2, okay, you are able to get the less than 1, means obviously whatever given amplitude of y, okay, if for example mod x by y equal to 0.5, what does that mean? My x amplitude is 50% lower than the y value. Am I right? So that will be the one, that is the region. So we want to design in this region. So what it means? My omega 1, omega n should be greater than root 2. What does that mean? Omega n should be smaller. Omega n smaller. So omega n smaller means square root of k by m should be smaller. So k by m should be smaller. Either k should be smaller or m should be larger. Right? If you look at it, the civil engineering foundation, they will try to do it. What they will do generally, they try to provide a foundation by increasing the mass to make it isolations. Right? All your machines, if you go to workshop, you see all these machines were try to place on some lumped mass. Right? The block is there. Right? What indirectly you are doing, the system natural frequency, you try to decrease it by doing this. Right? Your lathe machine is operating at 3000 RPM. Make sure 3000 RPM means, what does that mean? The frequency is 3000 RPM means by 60. F will become 50 Hz and omega equal to 2 pi F. That is nothing but 100 into pi. So around 314 radians per second. So I will make sure my omega n should be, okay, the rule of thumb generally for practical purpose, omega n will try to make it less than 3 times of the your excitation frequency. So obviously I need to make it 50 Hz, right? By 3 means around less than 16 Hz I need to make it. That is the concept we are able to explain by using the simple graph, right? This is single degree freedom. So what I am doing, either I increase the m or decrease the k. Decrease the k means I need a softer spring. So that is the reason if you look at it, nowadays the high-end buses, or you see the most of the high-end buses, they will write it air suspension. Okay, the public transport mostly leaf springs, the metal springs, the natural frequencies are not that much. But the road vibrations are low frequencies, maybe less than 5 Hz. So then obviously your spring, suspension spring, natural frequency should be, imagine for my road vibrations are 6 Hz. Okay, what is your bus suspension frequency according to these guidelines? Your bus suspension frequency should be less than 2 Hz. Yes or no? Because I have taken 3 from the designer point of view, but theoretically it's root 2. Okay, fine. It should be less than root 2 Hz. Means my springs should be soft. So instead of using the metal, what we are doing? We are trying to take a air springs. So see, high-end buses has a air suspension. The reason is the passenger will get a more comfortable positions. But there is a limitation how much weight can carry by these springs, and it should not be compressed, right? So those aspects will come into picture. So, but you can relate it air suspension, why this preferred from the rider comfort point of view, because of this, the road vibrations are at 6 Hz, we need to design the very soft spring, and the soft spring is obtained by the fluid that is like air springs. Even the tankers, whatever the military tankers, they use nitrogen as a suspension gas in their cylinders. Right? So what I mean is, yes, the gas-based suspension systems will try to provide for low things. Make sense? Okay. Okay. Then even in a frequency domain, what we'll try to do it, we'll try to measure the damping, not only in the time domain, even the frequency domain also we'll try to do it in terms of the sharpness. What we'll do at resonance, you will get a maximum amplitude. So we'll try to take it, the maximum amplitude will be 1 by 2 zeta. Right? This is the one. Right? How to get it? Just simple, you go back to your previous equations and substitute the here. What will happen? Your R equal to 1. This is 0. 1 minus 1 is 0. R equal to 1. So 2 zeta whole square and square root, it will become 1 by 2 zeta. So x by x static equal to 1 by 2 zeta at okay. Resonance. But here one more point I forgot to mention, especially in spring suspensions in isolated design, you look at it, this is the damping, right? The zeta is the damping one. As the damping is increasing, okay, as the damping ratio is increasing, the x by y ratio is increasing after root 2. Okay, x by y ratio is increasing. Just give a minute. Okay, just give a minute. Yeah, please go ahead. And actually, I'm in a class. Okay, please go ahead. Yeah, are you able to see my screen now?
Yes, sir.
Yes, sir.
Okay, so now what we are telling, the damping will be measured it. Okay, now you come back to the vibration isolation. What is happening here? By increasing the damping, right? By increasing the damping, my y by x, mod x by y is increasing after root 2. So now the question is, shall we need to include damping in the isolated design or not? Yes, it's an adverse effect after root 2. By increasing the damping, the x by y is increasing, right? So obviously it is not doing well in my intended design range, but still I need to apply damping. The reason is, when I'm trying to reach omega by omega n 2, obviously I have to cross omega by omega n is 1. Means I need to cross resonance. When I'm trying to cross the resonance, so the large amplitude of vibrations will happen. So I need to compromise. To minimize the vibration amplitudes at resonance. Right? I need to minimize that. That is the one of the important aspects. So that is the reason when you are doing the isolated designs. So you need to take care. So omega by omega n, right? So you need to cross omega by omega, resonance you need to cross. So you include the damping at the compromise of your isolation ability. Okay, that is another important point. Okay, now you see the sensors. Okay, the same problem, whatever you try to talk about base excitation problems, even you try to decide accelerometer and seismometer's working principle. Generally, what will happen in accelerometer, then there is a mass will be there, and there is it is supported by the two springs, and the dissipation capability is there, and whatever the base excitation is given, that should be moved, and a transducer output will do that. So what we are interested, whatever the input is given, that should become as output. So mod x by y should become tends to 1. Okay, mod x by y is supposed to be 1. Means my given input of the displacement, my output also same. That is the sensor duty. Sensor should not distort the measure end, and means measuring quantity should not be changed. So if you look at it, mod z by y, that is the relative displacement I'm calling. If you observe it, okay, if omega by omega n is very large, then the the relative displacement between the base and the sensor with respect to the given input of y, I want 1. Okay, then it's called as a seismometer. Whatever the displacement you measure, generally in earthquake, you will try to do that. The seismometers will try to use it. So to design the seismometers, what is the effective frequency range? Omega by omega n should be greater than 3. Okay, around this region, very high. Obviously, what happened? It tends to 1. Okay, to get that omega by omega n should be very large, right? Omega by omega n should be very large. So same logic. So omega n should go low, right? Then obviously m should go up. So that is the reason the seismometers are very large in size, bulk in nature, right? It goes for a large size. Okay, that is the one you will try to do it. And if we go to accelerometers, right? If you go for accelerometers, then obviously what will happen is accelerometers, what happen, omega square y will come. So it will become like this. Okay, I have not drawn here. It will be the close to 1 region, that omega square y region will come in the very low region. So omega by omega n is very small. Then it will try to measure acceleration. Okay, then omega by omega n should be very small, means omega n should be very large, means the k should be very large. That is the reason accelerometers is tiny in nature and it has a large natural frequencies. Okay, it has large natural frequencies. See, why I'm trying to give all these examples is by simple single degree freedom system problem, these helped us to understand the vibration control features, and it helped us what is the working principle of the sensors and isolators. So many problems can be solved it, and even what is the basic working principle in damping measurements also we are able to do that. Okay, yes, I have not gone through the details, but I'm giving a flavor why we need to teach single degree freedom system problems in our class. Is it has a lot of practical applications. So you relate them, then obviously it has a lot of implications on that. So just I will pause for a minute before going to the acoustics. Any questions? I'm ready to answer. Because I'm not going to the multi-degree freedom system at this moment. If I have any questions, I'm happy to answer. Any questions? Yeah.
What are the practical techniques for damping in the...
Sorry, I'm not able to hear you properly.
Sir, can you hear me, sir?
A little bit better. Yeah, tell me, sir.
Sir, what are the practical techniques to measure the damping practically? Damping measurement, sir.
Right.
Any given
that is a right. So there are, if you look at it, there is a system called O-buster beam method. Okay, O-buster beam method. So in a O-buster beam method for measuring the composites or any materials ones, generally the method they try to follow is same as the frequency response, sharpness measurement.
Okay.
Okay, and even for polymers, they try to measure by using the hysteresis loop. They try to generate this, that is called a dynamic mechanical analysis, DMA.
Okay.
Okay, so in our labs, we'll try to, when you are doing experimental model analysis, the model damping is extracted based on the sharpness measurement.
Okay.
That is off power point bit method.
Okay.
Yeah, but that is also coming from the simple single degree freedom systems.
Okay.
Yeah. So now I will in another 10 minutes, just I will give you acoustics one. Yes, these vibrations are generated in noise, right? I already started with that. So now noise, what is the parameters to be measured? Okay, what parameters to be measured? So are you able to see my screen? Are you able to see the presentation, right?
Yes, sir.
Yes, sir.
Yes, sir.
We can see your PPT, sir.
Perfect. So now the sound, as I said, it's like a nothing but we studied on our physics that says that a logarithmic, longitudinal wave. So it's a longitudinal pressure wave. It's a mechanical wave. Okay, it has a compressions and rarefactions, and it propagated with the speed of the sound. The speed of the sound is based on the medium. It's an air medium, means a gas, or like air medium, or a liquid water, or some other mediums, or structure like a steel. Okay, this is the one that we studied as part of our physics classes. So now what will happen? Yes, for sound to propagate, you require a medium, and it will try to propagate at a particular speed of the sound, and this will be the characterized in terms of the sound pressure levels and sound power levels. What is this? We'll try to look at it. So, for example, you go to market. You go to the market and ask them to buy a bulb. Okay, to buy a bulb. What is the question you will ask him, the shopkeeper? Should you ask him, give me 1000 candles bulb?
That's correct.
No, right? We'll ask him, give me 10 volts bulb, 20 volts bulb, like that. Am I right? Right? So how much power it will try to take it, that will try to do that. But you bring that bulb, bring the bulb, keep it in a room, right? Keep it in a room and see the power, the luminous powers, that is a candles. We'll try to cover 1000 luminous and those things. Is it same everywhere in the room or it will changes? The voltage is same. For example, you measure how much power current it has taken in a shopkeeper place and keep it in your room. The power is same, but it not changes. But the luminous levels will vary based on the environment and distance. For example, I'm sitting just below the light, just to sit up below the light, the luminous level, and far away from the light, right? The luminous levels are different or not? The same way, and the environment, you keep it in a closed room, dark room, and if you keep it in an open environment, okay, then obviously what happened? The luminous levels are different, right? Obviously, in these two cases, what will happen? In the same way, the amount of power the sound is generated by a particular machine in terms of the power is independent of environment and distance. It is independent of environment and distance. But the sound pressure, it's like analogy wise in like luminous, that will vary from the distance and environment. Okay, to get in better. For example, in a classroom, you are a teacher. The amount of power generated from your voice, mouth, from your throat will be same. But the students who are sitting in the front row and the students who are sitting in the back row, they may not feel the same sound pressure levels, right? And also the room is more echo is there, no acoustical treatment, echo is there. Then the environment also influences. Then that is the reason what will happen is, okay. So there are two parameters are there in one is acoustic pressure, sorry, sound pressure level. In analogy is luminous levels in a light, right? And sound power level. Okay, sound pressure level and sound power level. So the sound pressure level is dependent on I'm writing F means function of environment and distance, and this is independent of these two parameters. It's like a constant. Okay, it's independent of, I can call it constant. It's independent of environment and distance. Okay. Right. Now immediately the next question is, which is the preferred parameter for reporting? For example, some mix is making noise or some machine is making noise. Which parameter can be defined? Can be used for a measurement? Sound power levels or sound pressure levels? Ideally sound power levels, right? Because that is independent of environment and distance, so I can measure anywhere. But unfortunately, if you look at it, any typical, if somebody is mentioned about a sound information, you will try to mention sound pressure level SPL in terms of the dB. What is the dB? I will explain it at 1 meter distance. Okay, they will try to mention like this. Actually, this is the one is misleading completely from customer point of view. But why they are defining? The reason is measuring sound power level is not easy. Why it is not easy? I don't have any instrument to measure sound power level as it is. Only we have an instrument called the microphones are there to measure the sound pressure level. So obviously what I need to do, I need to measure sound pressure level in a known environment, at known distance. Yes, known distance I can try to define it by using the at 1 meter distance, 2 meter distance, then I put a scale and I'll try to measure it. Okay, I can measure sound pressure level in a known distance. But what is the known environment? What is the known environment? What is the known environment is? What is the known environment? Known environment is you take it a room There are two standard conditions we can think about it. Okay, there is a person is making sound, and it goes to the and reflect back. Okay, like this, it keep on reflecting. If you establish it such a way that you measure the pressure anywhere in the room, the pressure is uniform. You measure pressure anywhere, means completely reflected by the, that is the one environment that we called as diffusive field. That's called reverberation room. Okay, analogy is, for example, you do the bathroom singing, right? You see everywhere the bathroom is very small and you are trying to sing and you are generating the uniform pressure in the room, right? That is the diffusive field, reverberation room. The second case is, okay, there is no echoes. The second case is the sound is coming, it just goes, no reflections. Then this is called free field. So there is no echo, that called as anechoic rooms. So now what will happen? I need to establish either reverberation room or free field conditions by using anechoic room. Establishing these two facilities is not easy, very capital intensive. Okay, that is the reason. Okay, if you are defining a parameter, the user is not able to measure it, then there is no fun. That is the reason they try to measure in terms of the sound pressure levels and reporting the sound pressure levels. But at a R&D level, we can't use the sound pressure. We need to use the sound power. Is clear? Yes, there is alternative methods are there. That is intensity based techniques. Those things are there. Now, next is, okay, if I want to measure, this is the pressure. Okay, this is the pressure, acoustic pressure, and the rate of change pressure will gives me the velocity that we call the particle velocity. This is the pressure and there is a velocity, is a particle velocity. Pressure is scalar or vector? Pressure is scalar or vector? It is a scalar, right? Velocity is vector. So now we can think about it. What is the minimum mathematical operations you can done between the pressure and velocity? But arithmetic operation. We can add, subtract, multiply, and divide. So if I have a scalar and vector, shall we add them? We can't add. Shall we add or shall we subtract scalar and vector? No. But can we multiply? Yes. Can we divide? Yes. So I can do two operations, one pressure by velocity and pressure into velocity. So then pressure into velocity we call as intensity, that is a vector. Pressure by velocity, that is called as impedance. Okay, these two terms. Impedance, this is called as intensity. Okay, intensity into area called power. Okay, is integrated. Okay, this is the power. So see, this is the way. Actually, in acoustics, all our objective is try to get this pressure and velocity. So getting these two variables is our ultimate objective, either by mathematical, by solving the wave equations, or by measuring. So, but end of the day, our objective is getting the pressure and velocity. Once I know the pressure and velocity, I can characterize the complete system. I can talk about it and control that. Okay, so our ultimate objective is getting these two parameters, that is nothing but acoustic pressure, that is nothing, okay, and that is the pressure perturbation over atmosphere, that is a very small quantity, and velocity. Okay, so that is the reason. If you look at it, the typical sound pressure levels, okay, you see the linear scale first, and thermometer. Are you able to see the thing? Yes, sir, we can see. Yeah, you can see this side. The minimum threshold of hearing for a human being is 20 micropascals. Okay, these are micropascals. You can see the units. The minimum threshold of hearing. So you want to hear, you require 20 micropascals. And if you look at it in a typical bedrooms, those things is 100 pascals. Library 1000 pascals. In a group meetings, it's a 10,000 pascals. Traffic is like a 1 lakh, 1 into 10 to the power of 6. Okay, 10 to the power of 7, 10 to the power 8. You look at it, the beauty of this is like a 20 into 10 to the power of minus 6. This went to 10 to the power of minus 8, 10 to the power of 8. The range is very wide, right? So very wide, very small quantity to very large quantity. The beauty of all our organ sensor systems is they are able to detect it very minute quantity to the very large, strong variations. Imagine what are the sensor systems? You are talking, that is sound generation, listening, right? The smell, taste, right? Eyes. If you go to eye doctor, he asks us to read the letters, right? Those letters are in logarithmic in nature. The sizes of those are in logarithmic in nature, right? So that is the reason what we are trying to cover the wide range of 10 power of minus 5 or 10 power minus 6 to the 10 power plus 7 to wide range. We can't do it in linear scale. That is the reason we'll go for log scale. So when you do for log scale, okay, when you try to do the log scale, log, right? And what I'm measuring, ideally I can measure pressures, but pressures we can't add linearly. Powers can be added linearly. Pressure and proportional to the pressure square is proportional to the power. So that is the reason I will write it P square. But you can't apply log scale for the dimensional values. So we need to do non-dimensional. So that is where we will try to take the P reference. And this is a base 10. This we called as bells. That is nothing but Graham bell, right? So Graham bell is when you try to do the experiments in a long an electrical signal, small amount of electrical signal sending long distance. Okay, he was working these log scales. So to recognize his greatness, Graham bell that was one used. So 10 times you do that, that is called as a decibel. So we write it small deci, D capital B. This we called as sound pressure level. What is the reference value we can take it? So the minimum here threshold is 20 micropascals. That is the way we try to do it. This is called as a dB scale. Clear? So that is the reason when what will happen is if you try to add 80 plus 80, it is not a 160 because the logarithmic scales. So it will become 83 only. Okay. So this exercise I will try to do it. But what I will try to convey is acoustics is try to understand the sound generations, and there we'll try to use the concept called source ranking and try to do that. Okay. As part of the acoustics, you need to study the human perception into consideration, and you have amplitude and frequency both will come into picture. So those need to taken care. So yes, when you try to talk about acoustics, your background plays a critical role. Your background plays a critical role. That is the reason when you are doing a condition monitoring, the acoustic signals are not preferred signals because the environment don't have much control on you. That is the reason we'll try to use mostly vibration signals than the acoustic signals, because acoustic signals are influenced by the background, but vibration signals are less influenced. So that is the reason most preferred variable is vibration compared to acoustics. So with this one, I would like to quick summary. What we have done is today we were talking about it. Yes, the vibration generates the sound. All vibrations may not generate the sound, and vibration signals are more preferred for condition monitoring than the acoustic signals because acoustic signals are influenced by the environment. So and the distance you try to measure it. Okay, then second one, what we are trying to talk about it is, so that whatever we try to study as part of vibrations course, a single degree freedom system, it has a lot of practical implications. So you can understand the better on the what type of vibration control parameters can be done by using these fundamental equations. You can do that. So with this, I would like to stop it. Yes, I'm not able to do justice for the 2-3 credit courses, with 6 credit course. It's like around 86 hours in a 1.5 hour, but at least I want to give a glimpses of this topic. So I would like to stop it here, and any questions with the time permits, I'm ready to answer. Yes, sir.
Hello, sir.
Yeah, the people are
Yes.
coming to the
Any questions from?
Yeah. So, sir, thanks for the very nice session, sir. We would like to see this video later if we can get it. It was very nice. So the basics connection between the basic and the application, because now everyone is talking of applications, Industry 4.0, wherein sensors are being part of many of the latest machines. So therefore, these knowledge are very essential. Now, can you just suggest, sir, some of, suppose with respect to a mechanical engineering Industry 4.0 scenario, wherein some old legacy machines are being converted to Industry 4.0 system. So what type of sensors, again, it depends on the application. So can you give some thumb rules, sir, for that?
See, most of the times, like we'll try to do the 2 ways. Most of the times, okay, the output is the losses, right? If a machine is operating, efficiency is expressed in terms of the losses, right? the losses will be in either in temperature, right, vibrations and noise. This is from a condition monitoring point of view, right? And the performance point of view, what will happen? We are trying to take the energy, either in electrical energies or like hydraulic energies, whatever energies is there. So those parameters are trying to do. So one is sensing element. The sensing element, what you try to do, the sensing element, okay. Those are the regular sensing elements, but we are trying to talk about it, how to connect those sensing elements in a communication protocol. In IoT, it's more like a communication protocol. You try to make it integrated with the Raspberry and those communication IoT devices. You need to how to convert into cloud. Fine. That is the one part. Second part is the performance parameters. Like for example, I want to measure the torque, I want to measure the speed, I want to measure the current. So those cases we need to use the we need to use the basic sensors for the performance parameters. Okay, we are using those sensors, but those sensors are not compatible for the cloud. Okay, in a simple layman terms, imagine we have our 2G mobiles, right? Our 2G mobiles may not have access to the internet, but still it will try to do the basic function of communications, right? Our smartphones has a capability to interact with the means they can do the internet activities, smart activities, right? So those sensors will be replaced with the extra features which can have a provision for communication. Is make sense?
Yes, sir. Thank you, sir. If there are any courses of yours in the future or on YouTube, we would like to go through that, sir. Thank you very much, sir.
Oh, thanks for the comments.
Sir, I have one doubt. Sir,
yeah, please.
Sir, I'm from Veladri from Washington district.
Yeah, hi.
Sir, you talked about that air suspension, sir. Actually, in the suspension system, we use that nitrogen gas or something like that as a damper, no? Or so what is actually air suspension means?
No, because now simple, sir. You need not worry about all the how high-fi ones.
Okay.
You take a balloon.
Okay.
Take it a balloon. Fill with air.
Okay.
Right. At least you can keep it as some small kid on the balloon if it is a little bit bigger size.
Yes, sir.
Okay, you try to jump on that balloon.
Okay.
What is getting a spring suspension because the entrapped air.
Yes, sir.
Okay. Now what will happen? How? But if you try to the same balloon, if a big guy sits, what will happen? Okay.
It will burst.
So means the sprung mass will be the one of the parameter, but the filling air, other parameters, the cooling requirements and compressibility and all the things will be there. That is the reason I'm giving an example. Either people use the nitrogen gases or like inert gases and air also medium, because air cannot handle the large heat variation.
Okay.
Because it expands, right? Quickly.
Yes.
So maybe that is the reason you get a lot of non-linearity in your spring designs.
Yes.
Right. So that is the reason. What I'm giving is the analysis is like you can get the lower stiffness by putting the air entrapment or like a gas entrapment. The gases may be different. One of them is nitrogen.
Okay. Thank you. Thank you.
Thanks.
So thank you, sir. One more question can I have? See, all the systems are subjected to vibrations. Let us say we also go to some machinery wherein there is huge vibration. So the vibration is also transfers to human beings as well, right? So can you just brief on that, sir? What will be the effects?
Actually, that is the way human vibrations. There is as part of the environmental. Hello, are you able to hear me?
Yes, yes, sir. I think some are unmuted. You're clear, sir.
Yeah, what I'm saying is, yes, for example, the good example I can see that most of these drill bits used by the workers, right? For construction people. Hello? The construction workers use the drill bits, right?
Yes, sir.
So
audible, yeah.
The construction workers use the drill bits. You see the amount of large vibrations are coming on the on his hands, right? So his muscles will get a continuous high cycle fatigues. Okay, Then because of that, what will happen? You'll get a numbness in the things, and over the period you may get a means small cracks in his muscles, and even he may get a vibrations on the body. You know, this is the one technology. Thanks. Just I will do a small deviation. Actually, nowadays I think Google has released a product. Even if I don't have a proper hearing capability, but still even the sound comes, my skull bones will try to vibrate it for a given sound. So if I'm able to monitor the skull vibrations, then I can synthesize the sound, what type of sound is coming, the skull vibrations. Okay, just this again. But yes, the body vibrations, what happened, the impact on a human vibrations is one of the topic. Imagine your bike handle, right? The bike handle, whatever vibrations coming on your bike handle will really impacts the driver, that means bike rider, right? So that is the reason there are good number of the grip and material selection and how to avoid the vibration transfer to the handle. Those also is part of the studies. But I'm not really expert in the body vibrations and what is the human effect, that I'm not expert, but this is the applications I'm talking about it. But there is a separate topic, and there is a good book is there on body vibrations, and many places based on the application, they will give a limitations also. What is the acceptable vibration exposure levels? Okay, even similarly for sound also, what is the dosage you can give to the operator? If his dosage exceed, you need to change the operator.
Yes, thank you very much, sir.
Okay.
Sir, one gentleman posted a question in the message box stating that when we need to consider multi-degree of freedom systems for vibration problems.
Okay, good. See, when we are making an approximation as the lumped parameters, right, that will give me only one natural frequency, right? Only one natural frequency. But this is a continuous system. It's a continuous system. How many degrees of freedom will be there? Infinity degrees of freedom is there. So infinity natural frequencies are there. Okay. Imagine a simple thing. My natural frequency of a shaft. It's a continuous system. But if I use this lumped approximation model, my first fundamental only I'm able to find it out. My first fundamental is, for example, 10 Hz. 10 Hz means 600 RPM. But I want to rotate it up to 3000 RPM. Okay, I want to rotate up to 3000 RPM. So I cross the 10 Hz, means 600 RPM I crossed. What is the guarantee, or what is the assurance I can give as a designer? I will not get a second frequency. Is there any second frequency exist? Or third frequency exist? So in those cases, what will happen is then we'll go for, means that decides the same problem I need to convert back as a multi-degree freedom system. Okay. And in a single degree freedom system, I can't talk about a relative because there is only 1 degree. So how can I talk about relative? I don't talk. When I try to talk about relative displacement, then the mode shape will come into picture. So I need a multiple degrees of freedom. Okay. If I want to talk about mode shape, obviously I need to know the more degrees of freedom. So then we'll go for multi-degree freedom systems. Is it clear?
Then I have a very elementary question, sir. So whenever we talk about the fundamental frequencies or natural frequencies, actually, generally in multi-body dynamics, you might have, we say first fundamental frequency, second fundamental frequency, third fundamental frequency. But to be more precise, fundamental frequency is the frequency corresponding to the natural frequency. That's what the little knowledge that we have. Then why to consider the other fundamental frequencies?
Right. Actually, that is the small difference. That is not a fundamental frequency. Harmonics. Okay. For example, first harmonic, second harmonic, third harmonic, fourth harmonic, we'll try to talk about it. What is the harmonic? For example, 100 Hz and integer multiples of that. For example, fundamental is 100. Okay. The first fundamental is 100. The second harmonic is 200. Third harmonic is 300. Fourth, 400, 500, 600. Means it's a integer multiples of fundamental. Those are the harmonics. So when you try to rotate it any object, it will try to generate the signature with associated with the 1x. 1x means that rotational speed. If it is rotating at 3000 RPM, 50 Hz. Then corresponding harmonics means 3000, the corresponding frequency is 50 Hz and 100 Hz, 200 Hz, 150 Hz, 200 Hz, like that. Those are harmonics. Those are excitation frequencies associated with various problems like a misalignment, unbalance, and eccentricity, okay, looseness, okay, crack. All these will try to generate a multiple signatures. Those most of them they are dominated by the harmonics of the fundamental frequency. But natural frequencies may not harmonic. First mode, second mode, third mode, like that we'll call. Fundamental mode, second mode, third mode, fourth mode we'll call. We never call as a harmonics, right? For example, the system fundamental mode be 100 Hz, second may be 110 also, may not be the 200. Okay, that is the reason in the modes we'll try to talk about first mode, second mode, third mode. When you're talking about the excitations, it's a harmonic in things, then we are assuming first harmonic, second harmonic, third harmonic, fundamental harmonic, second harmonic, third harmonic, means 1x, 2x, 3x. So that is the way we'll try to talk about it. Am I right, sir? Is it clear? So don't mix when you are doing the rigid body analysis, the order analysis we are doing. Order analysis is 1x, 2x, 3x, like that. They are harmonics in a multi-body dynamics. In the vibrations, we are talking about first mode, second mode, third mode, like that. So the first mode may not have any relation with the second mode. Right?
Right, sir. Right, sir. And any questions from the audience? Okay, sir. Now I think it is the time to conclude the session. It's already overtime. You have already spent 20 minutes extra. And sir, anyone? Any questions from the audience? No. Okay, sir. Sir. Okay. So this is the audience are very much delighted to have the lecture from a passionate teacher. What we can conclude, and of course a willful consultant and very busy researcher. Sir, your lecture has thrown a light on vibration control and emphasized the importance of single degree of freedom system. Basically, what we people generally take it as very elementary thing, but the importance of single degree of freedom system you have highlighted. You have thrown light on even acoustics also. So it's a encapsulated, complete subject of vibration. What we heard in this 1.5 hours. And thank you very much, sir, for your time. And
thank you very much for giving me opportunity.
Sir, one gentleman.
Yes, and sir, one very small question posed just now. One gentleman is asking, a good reference for the fundamentals of vibrations. So, can you, from your side?
Thompson.
He's suggesting.
Theory of vibrations by Thompson.
Yeah, he's asking one good book for the fundamentals of vibrations.
That is the one I'm telling. Theory of vibrations by Thompson.
Yeah. Yes, sir. Okay, sir. So that's all for now, sir. Thank you very much for your time and effort, sir. And it's once again, we are delighted at your lecture, sir. And thank you very much, sir.
Pleasure.
Thank you, sir. Thank you.
Thank you, sir.
Yeah. Well, thank you all participants for your time, and please fill the feedback form before you leave the session. So thank you very much.
Thank you.